We are going to be talking about RC delay through and well. Depending on how long this takes, we might talk about something else today. All right, so since and wells have both resistive and capacitive characteristics, they can be thought of as an RC network. So effectively, something like this. So here is the profile of our well. Like so. And we are going to assume that we are going to have some potential difference across our well. So we'll just call the left-hand side the input port for this network, and the right-hand side the output port for this network. And as we move across our well, we have resistance. Like so, and then because we have a biased end well and our substrate is typically at ground, we are going to have some sort of depletion capacitance as well, where the bottom terminal of all of these capacitors is tied together at the same potential. So to be clear here, all of these resistors represent end well resistance, and all of these capacitors represent depletion capacitance that we've talked about previous.
Capacitance be uniform, will it change as you kind of get your wall versus wall?
So it will change. Sidewall capacitance is different than the bottom capacitance and all that kind of stuff. As we discussed, we are really, so this is getting into transmission line theory effectively. And so what I mean by that is that all of these resistances and capacitances are on kind of a per unit length basis. So we are no longer dealing with a lumped element RC network. We are dealing with a distributed element ladder network. And in treating it like that, we can effectively get through all those little problems that we would have.
So you don't actually have to break it down as this big RC.
Right. Yeah, we can work purely with effectively the information from the process technology node data sheet and plug those numbers in to our distributed network model to get what we're looking for to figure out the delay and things like that. Okay. A very brief circuits 1 style review here of what we should expect out of an RC network in general. So let's say that we had the following simple network. Here's our resistor. Here's our capacitor. This is our output voltage. And we put in a step function for our input voltage. What we would expect to see, and so this is our voltages as a function of time. And this is our time axis. So what we would expect to see is our input voltage waveform would look something like this in blue. And our output voltage look like this guy in red. We see some RC delay because it takes time for the capacitor to charge. That trivial, right? And we know for this simple RC circuit that our output voltage V out as a function of time is just going to be what I'm going to call V pulse. So I'll label that here. Just the height of the input signal times 1 minus, sorry, that's not a minus sign, e to the negative t over RC. Make my brackets prettier. Are just simple, straightforward, first order response for an RC circuit where we're looking at a charge cycle specifically. Okay. We are going to define some specific parameters here. Okay. So the first one that we are going to define is the delay time. So the delay time is the amount of time needed for the output signal to reach %50 of the input signal level. Or mathematically, we could say that 0.5 V pulse, which is 50% of the input signal, would be equal to V pulse times 1 minus exp of negative t over RC. And we can solve this equation or rearrange to find our delay time, which is the time at which this expression is satisfied. And this comes out to negative RC times the natural log of 0.5, which is approximately 0.7 times RC. Okay. So I believe it's actually square root of 2 over 2 times the time constant is what our delay time is going to be. Now we are going to define the rise time. For you guys, not write the letter M here. The rise time here. For whoever chose slew rate, this is effectively pretty damn close to how you measure slew rate as well. Okay. We're going to define the rise time as the amount of time needed for the output signal to increase from 10% of the input signal level to 90% of the input signal level. So coming back to our original graph here, if this is 0.5 V pulse, then let's do this in gray. This amount of time is our delay time. And if this is 0.1 V pulse, and this is 0.9 V pulse, this distance PR is our rise time. And that rise time is directly related to slew rate measurements. So we can actually figure out what the rise time is related to. Sorry, let me go back to that graph since I saw some people still trying to write stuff.
Just going for sure right there. Just have a no match. Call out a gray, I'm like, I can't believe I have a gray.
Well, at this point, I'm just arbitrarily choosing colors. I should have a piece of paper off to the side of me that's a legend for all the different colors I've used for stuff, but anyway. All right, so mathematically, we could say that let me switch back to black here. 0.1 V pulse will be equal to V pulse times 1 minus exp of negative t over RC. And from this, T 10% is going to be negative RC times the natural log of 0.1 excuse me, 0.9. And 0.9 times V pulse would look like V pulse times 1 minus EXP negative T over RC. From here, the time it takes to hit 90%, it's just going to look like negative RC times the natural log of 0.1. And then our rise time is T 90% minus T 10%, which will approximately be 2.2 times RC, the time constant for our RC network. Okay. So that's how things worked out specifically for a single first order RC network. Now we have to apply our transmission line theory. So as mentioned earlier, the NWEL RC network is a distributed RC circuit or transmission line. Similar to the one shown below. Over here, we have our input. This is R square. This is C square. We're going to consider this to be node A. Then we have another resistor R square. And capacitance C square. And this will be node B. Actually, let me do a third node here so we can figure out what the pattern is. R square, C square. This is node C. And finally, we're out here. R square, C square. This is node N. And here's where we're taking our output. So the delay time to node A is simply TDA is 0.7 R square C square. The delay time node B is going to be TDB is equal to 0.7 times R square C square plus 2 R square C square. So effectively, we're saying it takes time for the first stage to charge, and then the first stage charges the second stage, and then we have to recharge the first stage effectively. So it's taking time to propagate this signal down this ladder network, and it's going to be compounding for the increased number of nodes. All the way out to node C, we'd have TDC is equal to 0.7 R squared, C square, plus 2 R square C square plus 3 R square C square, etc. So, what the heck just happened? Okay, I mean, it seems to still be running. My screen is shared, so I don't know what happened. All right, so putting these results effectively together, the delay to node N is the total delay time. So we're just going to call that TD. And that's going to be 0.7 R square C square times 1 plus 2 plus 3 all the way out to N, which is an arithmetic series. So this is 0.7 R square C square times the summation from I is equal to 1 to N, and it's the sum of I. And that summation is the same as ½ N times N plus 1. Factoring out the 1/2, this looks like then 0.35 times R square C square N times N plus 1. And if N is very large, N times N plus 1 looks pretty close to N squared. Following a very similar derivation, the rise time for the distributed network is ER is equal to 1.1 R square C square N times N plus 1. All right. So let's calculate something here. Let us estimate the delay time through a 250 kilo ohm N-well resistor made with a width of 10 lambda and a length of, 500 lambda. We will assume that the capacitance of a 10 lambda, by 10 lambda square N-well to substrate is 5 femtofarads. So our delay time, TD, is going to be 0.7 times R squared C square N times N plus 1. We know what? C square. That's it. So we have to figure out everything else. So what do you want to do first? R square or N? That's the wrong choice. The reason why I say that that's the wrong choice is that we know the total resistance of the resistor. If we know N, then R square is just the total resistance divided by the number of squares. So let's figure out N first. Okay. So hopefully in a pretty straightforward fashion, there we have a width it's 10 lambda, a length 500 lambda. So using this, N, the number of squares, is just going to be 500 lambda over 10 lambda gives us 50 squares, right? So that's our total number of squares. From this, our resistance R square is 250 kilo ohms divided by the total number of squares, 50 squares. And so each individual square contributes 5 kilo ohms of resistance. From this, our delay time, TD, is simply 0.35 times 5 kilo ohms times 5 femtofarads times 50 times 51, which comes out to be approximately 22 nanoseconds. Let me write that out smaller so that it doesn't look like nanosiemens. Okay. So that's our delay time that's introduced. Now, this is using transmission line theory to figure out what the delay time is going to be. There's also a property called the intrinsic delay time that is related to the material. So effectively, based on the laws of physics and the material properties like the resistivity, or not the resistivity, the dielectric permittivity and things like that, how quickly is it physically possible for us to pass a signal through this particular material? Okay. The intrinsic delay time is mathematically given. So TID for intrinsic delay is the square root of the relative permittivity divided by C, speed of light in a vacuum, times L, the length. Okay. So if we're dealing with a silicon wafer, what is the relative permittivity of silicon? I believe it's either 11.9 or 16. You guys have Google? Give it a Google. My keyboard is unattached. I'm too lazy to connect it. Google the relative permittivity of silicon. $11.7. Okay. So epsilon R is equal to 11.7. C, the speed of light in a vacuum, is 3.0, really 2.998 or something like that. Let's just call it 3 times 10 to the 8 meters per second. If I am remembering correctly, our length here is the absolute length. And so what I mean by that is we can't have it in terms of lambda. We need a physical dimension to deal with here. So if lambda were 300 nanometers, then our length, L, is going to be, let's see, I think I said it was 500 lambda. Three times 5 is 15, and then I have a 0, 0. And then I have another 0, 0, and then I have nanometers. So that would be 150,000 nanometers is the same as 0.15 millimeters. So throw these numbers together in your calculator and tell me what the intrinsic delay time for this should be. I'm glad I didn't bring a calculator and I don't have it written down on my Post-it note. $1.71. So let's do this over here. 1.71 times 10 to the negative 12. Okay. So 1.7 picoseconds. That is how fast we could possibly send something. Okay. The Delay time of our ladder network is longer, so that's the true delay time. Now, if we were to do these calculations on metal materials and things like that, which if we have a long run of wire and we want to know how quickly we can send a signal down it, because the resistance of the wire is much smaller, even though it will form a capacitance with the substrate and all of that kind of stuff, we're likely to see that the delay time of the distributed RC network is actually approaching the intrinsic delay time of the material. Now, let's show one more quick little thing here, and then we'll wrap up for the day. It goes back to this approximation, okay? So we have our delay time is approximately 0.35 times R square times C square times N, the number of squares squared. If we broke this up as, let's do it in light purple, because I'm just trying to see how many markers I can make him pull out of his bag. If we broke this up, we could have this look like 0.35 times R square N times C square N. What does R square N represent? It's the sheet resistance times the total number of squares, so it's the overall resistance. What does C square times N represent? The total capacitance. So we don't actually have to lump, or we don't actually have to use the distributed parameters. If we know that we have a sufficiently large number of squares, we can use the overall resistance and the overall capacitance and get something that's going to be pretty close to what we would get using the transmission line network approach. I want to say it takes something on the order of 10 plus squares for these things to actually start converging towards something meaningful. But anyway. All right, so I think that's enough out of me for today. This seems like a good stopping point as we've only got about 10 to 12 minutes left, and that's not enough time to really get into the next topic. So we have spent 3 days talking about how to use or the various applications of our substrate material. Things are going to pick up a little bit from here. We should probably be able to finish up what our active region and things like that are used for. In a single day, metal layers might take 2 days, and then we'll get to polysilicon layers, which will probably take 2 days, and then we actually get into using full-on transistors and how all that kind of good stuff. So we're making good progress. Like I said, we are not going to have the lab class tomorrow because we handled what we needed to for today here. Use that time to talk with your group member and all that kind of stuff if they're available. Just pull, Google articles about how to measure these quantities that you've suggested you intend to do. All that kind of good stuff. My goal for tomorrow is to have all of the videos for this class completely edited and uploaded and available to you all, both on our Moodle page and my YouTube channel by close of business. That sound good? Oh, and also to have your first miniature exam thing up.